In this lecture, we'll learn the actual basis behind integration, the actual logic behind integration. Now we already know that differentiation gives you the gradient formula of the equation. And why does it give you the gradient formula of the equation? Because I have told you back in the differentiation chapter that the derivative formula is this: f of x naught plus delta x negative f of x naught over delta x, where the limit of delta x approaches to 0. And that's how you calculate the gradient at a point on the curve. Let's say this is our point P. That's how you calculate the gradient at a point on the curve, right? If delta x is brought, this is 0, is brought closer to 0, your tangent will lie exactly on this point, right? This also corresponds to the formula y2 minus y1 over x2 minus x1, right? This is delta y over delta x. Then we learned two basic ground rules of differentiation, that d by dx x of n equals to n x n minus 1. Now this was actually brought about by this formula. When you apply x of n right here in this formula, when you use this formula on x of n, in the graph of x of n, the answer you get is this, is always this. Hence we learned this way to derivate a function x of n rather than learning this formula. And this formula is also not in your syllabus. I'm just telling you this for your general knowledge. Alright, the same is the story or the logic behind integration. Let's say we know that if I'm given x of n dx, what I'll do is I'll do xn plus 1 over n plus 1 plus k. Now how did we actually come to this formula? How did we actually derive this formula? Now, as I've told you that integration is basically a process or a method to find the area under the graph. Now let me draw some coordinate axis. This is my y-axis. Let's say this is my x-axis right here. Alright, and let's say I'm in a car and that car is moving with a not so constant velocity. Let's say the velocity of the car is like this. Alright, so this is basically v, or you can get the f of x to. Alright, so f of x is v right here, and x is time in seconds. Now I wish to find the distance covered by the car from point A to point B, right? Now here's a problem, because we don't know that what shape this actually is. It is neither a rectangle nor a triangle nor a square, so we don't have any definite formula to find the area of the shape. And we know that area under VT graph gives you distance, and this area represented by the region enclosed by A and B is not following some definite shape. If the velocity was a constant, let's say if my car was moving at a constant velocity, let's say this, then it would have been way easier for me to calculate the area, because this would have been a rectangle. What I would have done is, let's say this is f of x naught, so the area if my car was moving with a constant velocity would have been b minus a into f of x naught, because it makes up a rectangle. But in this case right here, this is not a rectangle, this is something else. So what I'll do is I'll split the shape into numerous rectangles. Let's say this, and let's keep the width of each rectangle equal to delta x. Alright, of each rectangle. Now listen carefully. So the width of each rectangle is delta x, and there are n rectangles. Now if I wish to find the area under this region enclosed by B and A, I'll have to sum the area. I'll have to add the area of this rectangle, rectangle 1, rectangle 2, 3, 4, 5, 6, 7, 8 and 9 and 10. I'll have to sum the area of all these 10 rectangles. So there'll be some sort of a formula developed for this. We know that the width of each triangle is delta x, and let's mark this first coordinate xi, and this is our xn. Alright, so this will be f of xi. Height of the first triangle will be of f of xi, and height of the second triangle will be f of xi plus 1. Height of the last triangle will be f of x of n. Alright, so area enclosed by the region B and A of this blue curve, right, will be delta x times f of x of I, right? So by doing this, I'll find the area of this rectangle, this right here. Then I'll add summation mark from n equals to I. Alright, or let's say, yeah, from n equals to I till how many triangles are there? 10. Get it? So this formula will give me the total area of all the rectangles between A and B. But still, this will be just an approximate, not the actual area, not the actual distance traveled. This will be an approximate, because as you can see that there are some portion of the curve which are being missed out, which are being left out, these portions. So we're not actually calculating the area of these portions, right? So there must be some inaccuracy in our answer. It won't be the exact distance traveled by the car. If we were to measure the distance traveled by the car using a ruler or using any instrument from point A to point B, that would be larger than the distance given by this formula. So how to make it more accurate? Like, as you can guess, if I make more than 10 rectangles here, I'll get a better answer. If I make numerous triangles here, like let's say infinite number of rectangles right here from A to B, I'll get an even better answer. I'll get a better approximate than this one. Alright, so let's try that. This was my curve. This was the coordinate axis. Now let's draw the curve. This was our curve, and A and B, A, B. Alright, let's draw. So you can see that the more the number of rectangles, but all the rectangles must have the same width. Their heights are different, but all the rectangles must have the same width. The more the number of rectangles, the better our approximate area will be, right? The more area will be closer to the actual area under the curve. Our answer will be more closer to the actual area under the curve. So how about I do this? I take n was the number of rectangles, right? N was the number of rectangles. If I take n to infinity, what will happen then? I'll get the best approximate possible. So area, this is for the best approximate. This might only differ in some decimal points, in some decimal places from the actual distance covered by the car. N equals to I, we'll start from I, and we'll move till N, and we'll do delta x into f of xi, but limiting n approaching to infinity. Alright, get it? So this is the true logic or the actual formula of integration. Alright, when this formula is applied to the function x of n, we get this answer. Hence, we learn this, that when it is applied to x of n, we get this, instead of learning the actual formula, which is quite hectic. Alright, so we learn this basic rule, and the other one is, if it is a constant, let's say k dx, you get kx plus c. Alright, because integration is also the inverse of differentiation. I've already told you that. So the answer must be in such a manner that when you derivate it, you go back to this thing. For example, if I derivate kx plus c, I'll get k. If I derivate this, I'll get this. Alright? So I hope you're clear now about this. See you in the next lecture.